Hello and welcome everybody to the 3D Scanning and Motion lecture. Today we're going to talk about 3D reconstruction methods, following up what we have done in the previous lectures. So as usual, I'm going to start with a brief recap. So in the first lectures, we talked about what is 3D, like 3D representations, and how to obtain 3D. Specifically, we talked a lot about depth tensors, stereo matching, and then how do we use this kind of data and how do we store it. And then we had a couple of different representations such as point clouds, voxels, polygonal meshes, parametric surfaces, implicit surfaces. We also talked about how to go between these kind of representations. For instance, we had I gave you some homework to look at Poisson surface reconstruction, for instance, how to go from point clouds to polygonal meshes. We talked about implicit surface representations such as sign distance fields, and we talked about algorithms around it, how we can use margin cubes to take TSDF or an SDF and convert it into an explicit mesh. And we talked about raycasting sign distance fields in order to render the images or depth maps directly. So today we're going to follow up on these things. We're going to talk about 3D reconstruction methods on top of it. We not only going to talk about reconstruction methods though on top of the point clouds and representations, but we're also going to talk about different types of reconstructions from various types of inputs. So maybe let me start with an overview here to give you a little bit an intuition what I mean with that. So there's different types of 3D reconstruction methods. So what we have already been talking about was mainly the thing here on the bottom. So we talked about depth cameras, right? So we talked about how can we basically get a depth frame if we have, let's say, a calibrated stereo camera, or if we have like a Kinect or something like this. So you should know roughly now how these kind of cameras work and what we can get out of it, what advantages they have, like do they work indoors, outdoors, do they need active projection? Do they just do passive stereo and so on, right? So these depth cameras we talked a little bit about, and but there's of course other ways to get 3D. So one might argue, well, you could use multiple images, right? You could just say, well, I just take a single camera, I have a static scene, but I take multiple photos of this environment, and then I want to do some sort of 3D reconstruction around it. Now, there's also ways in principle to go and take single image reconstruction, but I have to say this is an extremely ill-posed problem. I'm not sure how much we're going to cover it in this lecture actually, maybe slightly, but single image reconstruction is, traditionally speaking, it's not an easy problem, of course, because it's under constraint, meaning that there's, for one image, you can have many different explanations in 3D, so hence it's a bit of an ill-posed problem. However, there are methods doing this. You can, for instance, use priors, right? You can use machine learning methods to learn what is a plausible 3D scene based on an image. This one up to date has been a lot of research, and the true answer is probably none of it works convincingly well to use it in practical applications yet. Still open question, but high level is the learning-based methods are really cool. We can do a lot of stuff with it, but most of the part you have this issue that up to scale you don't know what's going on in the scene. There's also methods like shape from shading. So here the idea is basically you're exploiting kind of an inverse graphics pipeline, right? So you're kind of saying, oh, based on the appearance in the image, there must have been some sort of way how the shading was computed there. In this case, the shading is by the real world, and you're using a shading model, and then we're trying to inverse reconstruct how the surface should look like. Also not so easy. Also a lot of priors, even in shape from shading methods. Some of them learned, some of them by handcrafted priors, but not so straightforward. Okay, today we're mostly going to look a little bit at these kind of things. Multi-camera setups is one option, or what I said is like if you have a single camera, but you have a static scene and you take multiple images of that static scene. Okay, so yeah, so we have, we have seen basically so far. Yeah, I wanted to follow up on this. So we have seen basically so far range sensing devices a lot, right? And the idea, what they do is, they do basically this part in the middle here. They also use multiple images. But there's different ways how they use multiple images. So one option in a stereo camera is you have two images and you're going to do passive stereo imaging between those. So either you have these two cameras, or you have a projector and a camera setup, right? And in this case, you kind of still have you always need these two optical sensors. Right? If it's a projector or in a camera or two cameras, that doesn't matter too much. Well, it does matter from a technical standpoint. Algorithmically, it's pretty similar actually in a sense. But basically, you always need these you need two optical sensors basically in order to obtain quote unquote actual depth data. The rest is just hallucinated depth for the most part. And yeah, we have seen stereo, structured light, right? These were the common examples for that. Laser scanners, very simple ideas, same thing, right? You have basically the laser beam, and then you're going to have some sort of camera that captures. Okay. Now, I want to talk a little bit about multi-view reconstruction, and one probably the most simplest but also popular method is visual hull carving. And it's a relatively straightforward idea. So the assumption is what we're making here is we assume we have a calibrated multi-view setup, right? So in this case, here's 3 cameras, 1, 2, 3. We're going to have 3 images for these cameras. We know the intrinsic calibration of the camera, so we know the projection matrices, and we know the extrinsic calibration between the respective cameras, right? So we know how to go between the relative spaces between all of these cameras. So let's just assume these are RGB cameras, right? So they capture 1 RGB image per frame. And let's also assume we're going to have some sort of object segmentation, right? So meaning that the object of interest is the only thing that we have, and the rest we can kind of mask out. So if we have kind of a green screen setup, right, we can very easily say, oh, everything in the background is going to be masked out, and only the pixels on the objects of interest are going to be like not masked out, right? So this is the idea of visual hull carving. And the idea is relatively straightforward. So based on the intrinsic camera parameters, you can kind of take the silhouette around the segmentation of these objects in RGB space and shoot these rays kind of along the silhouette. And what you know is everything that is kind of outside the silhouette is actually free space. So let me try to illustrate it here, right? So if you, for instance, you have these 3 cameras, right? You have here the camera frustum from this camera. And here's the object that you're seeing here. This is the segmentation. You know, all the blue stuff here is outside the silhouette. This one is outside here. This one is inside. So what you know is everything here that is left to this ray on the silhouette, like everything here, you know is free space, all right? So what you do is you just say, oh, there's nothing there. And for the interior part, you don't know for sure, right? Because for the interior part, you might, like, you know that, oh, there was an object somewhere in between here, but you don't know the depth of it. You don't know how far and how close it is to the camera, respectively. But now the idea is, you're not only having 1 image, of course, in this case you have 3 images, and from these 3 images, you're already getting way more constraints of voxels you can quote-unquote carve out. So this is this visual hull that you're carving out here, right? So you know these ones you can carve out, this part here you can carve out, this part here you can carve out. And if you're doing this with these 3 cameras, you see that only this shape here that was of interest here in the middle remains. You also see very quickly is this is not perfect because you're missing a bunch of pieces here. Like for instance, if this was a circle at the beginning or a sphere in 3D, you didn't have any cameras that said, oh, this part here has to be carved away, right? But here on the front part, it's actually fairly accurate, even with only 3 cameras. And the more cameras you're adding, the more accurate the visual hull carving goes. Now, how do you do this actually in an implementation standpoint? Well, so what you do is here you have basically a voxel grid, right? And the most naive thing is what you do. You're just going to go ahead and say, oh, every voxel outside in this free space region, you're just going to set to 0. And everything else at the moment, you're going to set to 1, right? And whenever you have a 0, you keep it to 0, even though you had a 1 before, right? So basically the carving dominates all. So once you know 1 image that carves away something, you know that this is gone forever, right? So you can, so if you're adding more cameras, you will reduce the occupied voxels more and more, and you never get voxels back. And now it's going to be pretty interesting what you do in these boundary regions. I'm not going to go into all the details, but I wanted to give you a bit of a high-level overview. So now on these boundary regions, you can try to do something a bit more fancy, right? You can try, because you're going to have some aliasing and stuff like this. So in these boundary regions, you can do some sort of smoothing, you can do some sort of interpolation and so on, in order to get something that is a little bit better than just treating pixels as a harsh criteria to carve things out. The other thing you might notice is once you have one segmentation error in the 2D images here, they're going to carve out a lot of stuff. So if you have one pixel accidentally not being segmented out, that might cause a lot of problems. So you might also have to deal with outliers. And the way you could do this is basically just count how many cameras have seen it outside and inside. That's a straightforward thing. You can do some robust optimization. All of these kind of things could help. Again, I'm not going to go too much into detail, but I just want you to know that there's a couple of practical things you can do in order to avoid these kind of outliers. Okay, how does it look in practice? In practice, you're going to have a setup like this one here. So, right, so here we have all the input images at the top. And all of these images, as you see, they are basically recorded in front of a green screen. So based on this green screen setup, you know, every pixel that is kind of greenish, you can kind of segment out. These are the binary segmentation masks here for every view, right? And now what you can do is you can go ahead and do setting up your voxel grid. These cameras here are going to be calibrated. And what you can do now is you can do this visual hull carving. So this scene actually, right, this one here, gives you approximately this kind of shape, if you do this very naively. And this one was, I think, with 11 cameras, and this, I think, I don't actually know what these numbers mean anymore. I think this might be a smoothing kernel, but I think they always have 8 cameras actually. But basically the high level idea is you have, this is a naive thing, you see that you have a bunch of like noise here because the segmentation wasn't perfect, and then there's like a bunch of smoothing kernels. I think this is the smoothing kernel size here at the bottom. But then you have a bunch of smoothing kernels in order to improve the quality here, right? So even this is very naive here, and it looks a bit noisy, you can actually get a semi-reasonable surface here out of it, right? It's not great, but it's very straightforward to do. It's very easy to implement. You have a bunch of smoothing stuff on top of it, and that's roughly what you're getting here, right? Yeah, this setup that was used in this loop paper in 2013 was basically focusing on making stuff real time and very fast in terms of reconstruction. Like if you compare this to other reconstruction methods we've seen before and what we're going to see later on, this is actually darn fast, right? You can implement this probably even on a phone in real time. It's very straightforward. And the setup they used looked something like this, right? So they have basically here, they have the cameras here on top. And this is the real-time reconstruction they're getting out of it as they go. And the nice thing is you can relatively easily texture that too, right? Because you basically have one-to-one mapping between the 2D and the 3D stuff. Here's another example. It's not perfect, right? You see a couple of artifacts sometimes, but on a high level, the reconstruction actually looks pretty good. You can even do things like hair and so on, because you can simply map them the texture on top of it. I should, however, say this is possibly a little bit, well, I wouldn't say misleading, but it looks very good because the texture looks pretty good, where the geometry could be still improved a little bit, right? Yeah, so these are the kind of reconstructions they're getting. And again, this works in real time, very straightforward, can deal with things like hair and so on, which we will later see. Hair is not easy. Hair is not an easy reconstruction. My hair might be easy, but long hair not so easy. Yeah, this is the geometry. You see the geometry actually looks very basic, but you can still use it as a proxy geometry in order to get a very nice texture field on top of it. Okay, the interesting thing is this visual hull carving, this can be expanded to space carving basically, and that works actually also with depth data. So the core idea is you just need to fuse the data from fuse, and you need to somehow handle the noise. This is challenging, I mentioned this, but there's a way to do that. But the idea is, when you're using the depth data, you're not only now carving out this kind of stuff as free space. If you have depth here, you would carve out also the part in front of the depth values. So behind the depth values, you don't know what to do. But in front of the depth values, you know that there's nothing there, because otherwise this depth value wouldn't be there, right? So, and this is a very important concept. We're going to call this free space carving. And we'll see this later a couple of times, that this free space carving is actually quite important for many types of reconstructions in order to add additional constraints. Even learning-based methods today use that. But yeah, so the idea is kind of, we have kind of here, we have now the silhouette that says, oh, this has to be free space carved. And we know that the depth value here says everything in front of this value also is going to be free space. And now you're doing this on every view. And then you have more constraints than if you did it just from RGB. So as I said, like, there's a bit of challenges in terms of dealing with noise, and there are ways to do it, but it is not so straightforward actually, right? So if we are summarizing about visual hull carving, space carving, conceptually it's a very, very easy method to deal with, right? Because you just have a voxel grid, right? And you just mask out voxels that are in some sort of free space area. And that's it. That's basically your method. The big downside of visual hull in space carving is that you need these required multi-view setups, basically, right? So in that case, somebody has to go ahead and construct the setup here, right? They put a bunch of cameras here. It's super expensive. And even like for this like super expensive setup here, you basically have to calibrate everything, which is also not so straightforward, right? You have to go ahead and compute the extrinsic. Somebody hits your setup, you have to recalibrate it and stuff like this. So extrinsic calibration, not so straightforward. It's also not so robust to noise. I mentioned that there's a few things you can do, but still not so easy. But I wanted to mention it anyway, because I think it's super important for the conceptual understanding of how multi-view reconstruction could work, and possibly then later on how to integrate these kind of things like free space carving and so on, right? So I think this is kind of important. Quality could be improved. With multi-view stereo setups, you can get better quality than this, but this is conceptually, I would say, the easiest one to get started with. Okay. All right. So now let's move a little bit further and let's try to relax these constraints. So now we don't want to necessarily use these calibrated setups, but we want to do some sort of reconstruction from multiple images taking over a sequence of times. And this is essentially what structure from motion is doing. And structure from motion, this is actually something that is very widely used for a lot of practical applications. And in this case, the idea is what I mentioned, right? You have a bunch of images. These images can be unstructured. Could be with the same or different cameras. I'll get to that in a second, what that means. And this is a method that is really widely used. So often SFM is the short acronym for it. If somebody tells you, hey, I work on SFM in computer vision, then everybody knows you're working on structure from motion. So it's very, very popular. Okay, so what's the idea? The idea is basically we're having these images. So let's say we're taking 3 images of the Colosseum from Rome here. And you see these images are completely taken at like different weather conditions and different views and so on. And with these images, the goal is to do 2 things. We want to figure out A, the 3D points, basically these ones here. And B, we want to figure out the camera positions. And in order to make this thing work, we have to do these 2 things simultaneously, right? For instance, if we had these 2 images and we did know the camera positions and we did know the intrinsics, we could just do a stereo match, right? But we don't. So we have to do it simultaneously. And this is kind of this structure from motion idea. And on a high level, the way this works is the following. So you're going to take a bunch of images. Ideally, you want to have high quality images, otherwise it doesn't work so well. So higher resolution, less motion blur, less depth of field, stuff like this is not very helpful. So clean, high resolution images, that's what you want to get. And the first step is you want to detect a bunch of key points in an image, and I'll get to a second what a key point means, then we want to find correspondences between these images. So now we want to find matches that say the key point in this image matches with the key point from the other image. And then at the end of the day, once you have correspondences, we're going to formulate this as an optimization problem that for each image I, we're going to have a transformation matrix Ti, and then given all matches, we jointly solve for the transformations Ti and the 3D locations of the points xj. Right? So this is the idea of structure for motion. Take a bunch of images, detect key points in each image, find correspondences between the matching key points, and then figure out the optimization at the end. And there's maybe one thing I want to mention here. I mean, I'll try to explain it a little bit later. So before I go into how this actually works, one might ask, why is it a good idea to find correspondences between key points and not just correspondences between every pixel? And the idea here is that if you were having points that are discriminative, meaning they have some sort of special feature that makes the matching easier, then the overall combinatorics between this matching problem go down. Because the whole thing is revolving around, can you find matches between points? And the idea of having key points and distinctive points rather than any arbitrary pixel is that you're going to get the dimensionality down, right? So if you have two images, let's say each image has 1,000 times 1,000 pixels, right? So you have 1,000,000 pixels. Then you have 1,000,000 times 1,000,000 different combinations of how to match correspondences between these two images. And that's way too much, right? And because of that, people go ahead and say, oh, what if you only have a few key points, let's say 20 key points in each image, then it's only 20 squared kind of combinations, right? So basically the idea is using discriminative features at key point locations is computationally more tractable than trying to do like a dense correspondence matching, which is just brute force and would be not practical. And because of that, it is actually fairly important how to design these key points, right? So it's very critical that basically key points are distinctive and discriminative, right? So they have to, in a certain region of an image, they have to define a discriminative feature. And the question is, what does discriminative mean in this case? Well, discriminative means that it's, if I have basically two images, what I want that this key point here is also going to be a key point from a different perspective, right? And typically what people do there is they examine the local gradients. Local gradients could be, for instance, a corner point, right? If you have a corner point, this key point detection, corner points is very popular in a sense, because there's a corner means, oh, there's local maxima in the descriptiveness of the feature, right? If you have a white wall, that's the opposite of a corner point. A white wall has no discrimination. And there's a couple of very common key point detectors that kind of do that. There's Harris corner detector is very popular, Farce corner detector is very popular, Shitomasi corner detector is very popular, Sift detector obviously, and I wanted to go a little bit into that. But before I go into each of the specific them, I want to reiterate what a good key point detector should do. If you have basically two or more images, you want to make sure that a key point in image 1 is also going to pop up in the other images as the same physical point, even though the image was observed from a different perspective. And the core idea behind all of these ones is most of the time you're trying to find local maxima in the gradients. And for the most part, this is one way or another one to look at the corners. And there's various ways now how to do this efficiently. So let's start with a very straightforward one. Let's start with a fast key point detector. So the fast key point detector is really straightforward. So you're just looking for local maxima basically in the gradients. So the way this works is, so you're picking a point P in the middle here. This is our point P, right? And now what fast says is have a kernel around this point P, right? And if these 12 pixels in this circle around here are brighter than P plus a threshold, then this is going to be a corner, right? So right, it's very straightforward. You just say, is there a local gradient change? Am I as the point P, am I a local supremum in this area, right? And that's what I'm trying to figure out by looking at the in the intensity space, right? So I'm just saying, is based on this kernel here, is P discriminative? And in principle, this is fairly arbitrary, right? You can define these kernels in a different fashion too, but the high-level concept is always the same. Like, am I as P, right? Am I gradient-wise very different than from what my neighbors are going to be? In this case, it's just looking at the brightness of the surroundings. You have this hyperparameter threshold here that says, oh, like what does make, like how many key points do you basically want to have is defined by this threshold here, right? If this threshold is 0, then everything is going to be a key point. If this threshold is very high, it will have very few key points, but possibly more discriminative key points, right? And if you're running the fast key point detector here, you're going to get results that look like these ones here, roughly. It's not well, it's not super sophisticated. It's very straightforward to compute, right? It's just looking at this local kernel, and it gives you some decent results in principle, right? Okay, so this is kind of the simplest key point detector you can have, right? So locally, you're just looking for discriminative features. The next one I wanted to look at is the Harris key point detector. In principle, that's the very same idea, except that the way to determine whether my local point is an extreme point in my image is just computed a little bit differently. And the way you do it is you basically having an image again, right? And in this image, you're having a window function. You're having a shifted intensity minus the intensity of the current point. So you take a point X and Y, you take the intensity, you shift this point in the local surrounding here, right? And based on this function E here, you're computing now, you're parameterizing U and V, right? U and V is basically the shift offset that you're having here, right? And now what you're going to do is you basically have this matrix M that encodes this function here, right? It's just UV times M times UV. And you're just writing this whole thing here as a matrix form. This is the matrix you're getting. So this is like, this is the respective gradients now that you're having, right? Because this is through the shift function, you're getting these gradients here. And now what you're doing is you're simply computing, you're completing this R here, and I think it's basically stands for response. So you're checking for this corner response, right? This is the determinant of this M matrix minus K of the trace of M squared. And now what you can do here is you can just check what R is going to be in practice, right? So if R is small, then the region is flat. That means your eigenvalues, lambda 1 and lambda 2, are going to be small. If R is smaller than 0, then the region is an edge. In this case, lambda 1 would be greater than lambda 2. If R is large, then it's a corner. Then lambda 1 and lambda 2 are going to be large, right? So basically, in other words, what this is doing, right? It's looking at the eigenvalues here of this matrix M. And the idea is that if both of them are going to be small, that means there's not a lot of variety in this window function here, right? And the idea here means if you have a lot of variety, you're going to get large eigenvalues. If only one of them is large, then you know it's going to be an edge. And if both of them are large, then it's going to be a corner point, right? Then you have variety in both X and Y dimension. And this is actually relatively straightforward. So all you're doing basically is looking at the at how locally the gradients are changing in X and Y direction. Are they changing in both directions? Are they changing only in Y directions? And you can compute this analytically by using, like, looking at this matrix M here and checking the eigenvalues here, right? And yeah, you can kind of encode this one here like this, right? Where these thresholds are is, I think, fairly arbitrary. But basically, if both of them are small, then it's a flat region. If one of them is large, if lambda2 is greater than lambda1, then it's an edge. If lambda1 is greater than lambda2, then it's also an edge. And if both of them are large, then we know that, yeah, then E increases in all directions. That means we have high gradients in every direction from the current point. Then we know it's a corner point, right? And this is basically what Harris corner detector is doing. We're looking for points ideally at the top right here. There's of course a threshold now, how much we consider, but basically looking corner points in these regions. Okay. How's it look? Okay, so this is basically how detection works. Harris is something that a lot of people use. I don't want to go into all other ones. In principle, they're all doing the same thing, right? They're looking at local gradients. They have some way of computing it. Harris is doing it via the shift function, basically. And you're looking how the intensity changes locally. You're computing this matrix. You're computing the eigenvalues. You're checking if there's, like, basically, you're kind of parameterizing locally the change of intensity. And if the change of intensity is high, then you, in all directions, then you know it's a corner point. It's okay. And this is an example here, right? You have these checkerboards. Then here Harris works perfect because checkerboard is really easy to do. And then you have this one here is this example that we had previously, right? This is the same example here. You see actually fairly clean key points that you're getting out of a Harris detector here. So Harris is very good at this kind of stuff. Okay, so these are a couple of ideas how to do key point detection. And again, the high level idea is we want to find discriminative points that could be matched afterwards between frames, meaning that the key points should be points that we find in both frames. But now we have to figure out how do we match those ones. And this is the feature matching or the correspondence matching part, right? So first thing what we did is we detected points with a key point detector. Again, Harris, fast corner point detector, stuff like this is very standard that people use. And now we want to figure out that this point and this point is in fact the same point, right? And so on. So we want to find correspondences between all of these detected key points that we have found. So obviously this is a relatively easy example, but in practice, like this is a very easy example, but in practice you're going to also get key points that are in the left image but not in the right image, right? So this is like here we have well, how much? 2, 4, 6 points in both images, and there's a bijective matching possibility between those ones, right? Okay, so this is what we want to do. And we want to, the key points we've talked about, matching we haven't talked so far about. And this can not only be done between 2 images, but you could also think about this between many images. So for instance, here we're going to have one point. See this red little dot here, not my laser pointer, but this part here in the middle. This is my point, and this point has been seen from here, from here, from here, from here, from here, from here, and from here. So this point has been seen from many views, and this is not just a stereo matching problem, this is a multi-view correspondence matching problem. And this is practically what structure from motion has to solve, right? So we're having these key points in n images, and then we want to find matches between all of these images, ideally. So ideally, we want to find every point in every image, right? This would be the high level idea what we're trying to do. Okay, so now there's this high-level concept of features, right? I mentioned this a couple of times. What is a feature going to do? What is a feature even, right? I always said, oh, this has to be discriminative, like a point has to be discriminative such that we can compute good features. But what are features, actually? This is maybe, if you're new to computer vision, you might ask the question, like, what are people talking about when they're talking about features? In the concept of neural networks, people also talk about features all the time. In this concept of structure from motion, a feature is typically around key points. It doesn't have to be around key points, it could be anywhere, but in principle you're doing it around key points. And the idea of a feature is that you're mapping a high dimensional space to a lower dimension. Okay, what does that mean? So for instance, a very naive feature is a sum of squared distances, right? So we have this SSD function, so right, this is my point here in the middle, I have this 3×3 neighborhood here, I have the 3×3 neighborhood here, and I just literally compute the L2 distance between those pixel intensities, right, or between these pixel color values, right? This is what SSD is doing, right? And if this SSD value is low, then my sum of squared distances is going to be low. That means my feature distance is going to be very small. So, right, my feature distance is nothing else but an L2 distance right now between between adjacent points. And the challenges, of course, with that is this SSD function. This is a very naive feature. This is like the most naive feature you could imagine. But in practice, it's not a very good feature for multiple reasons. First, it's not very easy to compare, right? And this is like mapping this high dimensional space. You would rather map this to a lower dimensional space, right? So imagine this kernel was larger, it grows quadratically, right? So if you have like a 10 by 10 kernel here, then you're having 100 pixels times 100 pixels. So you have 100 pixels on one hand and 100 pixels on the other hand, and you want to compare those ones. And the other thing is this feature is not very discriminative, because if you have this 10 by 10 kernel and this kernel is just shifted by 1 pixel, your feature distance will be very similar even though you shifted the point. And this is not something you would want in practice. So what are the features not doing? The features is basically an idea. You take this kernel of this neighborhood of pixels around a point, you're mapping this high dimensional space here around this point here to a lower dimensional space, such that you're doing then a comparison in this feature space rather than in this existing high dimensional pixel space what we had before, right? Okay, and the properties or the idea behind that is that this comparison is easy. And the easiest comparison you would like to do is something like, well, let's say we're mapping this 256 squared area to 128 dimensional descriptor. We just want to do something like a dot product between those two features to compute a distance. That's easy, right? That would be great, because then I just do a dot product between 128 rather than 256 squared, which is like orders of magnitude less compute to do. And I can do this very quickly and figure out when my distances are low and not low. But there's a few more ideas behind it. So there should be a few properties on these feature descriptors that I want to go over. And this is very important if you want to design your own descriptor, or possibly later when you use machine learning to learn some of them. This is in principle what you would like to get at. So the idea what I already mentioned is the speed is kind of important, because otherwise you have this kind of brute force complexity issue. You want to do fast comparisons also, right? You want to go in a, let's say, a dot product in the feature space. Could be easy with a KD tree, right? You just find the n nearest neighbors to do feature matching. But then here are the 3 important things you need to know about good features. If you have a good feature descriptor, it's scale invariant. What does scale invariant mean? Well, if I have this image and I zoomed into the key point and I computed the descriptor again, I ideally want to get the same feature descriptor, the same 128 dimensional vector or whatever that I had gotten before. Same thing with view invariance. If you're looking at all these images, they all see the same point here, right? Ideally, the feature descriptor of this red point and 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 so on, they should all be identical in feature space. If you're looking, for instance, just in the RGB color space, there's no way they're going to be similar, right? They're going to have very different colors in the surrounding. So yeah, they should also be lighting invariant ideally. So for instance, if you have a little bit of, like if you have, the extreme case would be daylight versus night. That's a bit too harsh. I think that's not doable with practical features. But if you have small lighting changes of view-dependent effects, you want to have your features being invariant to that as well, right? And these are kind of the ideas that drove the community, the research community, to figure out various types of features. So we wanted to explain a few of them. So very common features is SIFT. SIFT is probably the de facto standard what most people are using. There's SURF, which is an alternative to SIFT. There's Orp, Freak, and many, many more. So if you're looking up feature descriptors for 2D images, you will find probably thousands of papers. It's very, very crowded area. SIFT is what I said is probably, well, kind of this gold standard of feature matching. Surf is an alternative to SIFT, and I mentioned this as an alternative because there was a time when SIFT was patented, nobody could use it, and people were using Surf instead. Orp and Freak are much lighter weighted descriptors, so if you want to do something faster to compute the descriptors, then Orp and Freak are going to be a bit easier to do. And nowadays, and by nowadays, in the last 5-6 years, people started using machine learning in order to learn these descriptors rather to handcraft them. And I'll get to this in a second, how you could learn them and what kind of network architectures would you actually use. And there's a couple of examples like MatchNet, Lift. Lift is like learned. It's like a learned version of SIFT, or 3D Match in 3D, for instance. That's something we've done. But yeah, there's a lot of like learning-based methods. There's also a lot of them, and there's an argument why it makes sense to learn it. Okay, so let's have a look at SIFT first. And SIFT is short for Scale Invariant Feature Transform. That's kind of like, this is inherently designed to be scale invariant, right? And the idea is, what they do is, they basically have, they take the image at different scales, or sorry, they take the neighborhood around, they first take a key point, and around this key point, they take the neighborhood of pixels, and they take different scales of this neighborhood. So they have kind of this hierarchy. In SIFT terms, they call this octaves, but this is nothing else but a multi-resolution representation. And they kind of hard code the scale invariance this way. And then what they're doing is, instead of like matching color values, they're taking difference of Gaussians. So they're taking a Gaussian, so for one octave, for one of these scale levels, they're taking a difference of Gaussians. To this end, they're dividing the neighborhoods into 16 subblocks. And for each of these subblocks, they're computing 8-bin orientation histograms. And from these, they are then getting 8 times 16 dimensional outputs. And this is this 128-dimensional feature descriptor that is often used for SIFT. So in principle, you could change the dimensionality. This is just what a lot of people are using today. But in a sense, 128 is kind of arbitrary, could be also a different number. But the idea is then, once you have this 128-dimensional descriptor, you could go ahead and do a dot product between the feature vectors that tells you how close do these 2 points at the center where the descriptor was computed actually match in practice, right? So SIFT is, as I mentioned, it's one of the gold standards in feature matching. It's extremely costly to compute. Well, extremely costly is maybe a bit of an exaggeration, but it's relatively costly to compute. But it's also relatively robust. So out of these descriptors, what I just mentioned, if I'm going back here, like SIFT, Surf, Orp, and Freak or so, like these kind of feature descriptors, SIFT is typically being used if you want to have high quality. So if you want to do some offline reconstruction for a structure from motion, you typically want to use SIFT for the most part. I also wanted to go into, I wanted to quickly, of course, I'm hiding a bunch of details here, right? Like this is there's a lot more details in the implementation here, but the idea is very straightforward, right? So you kind of realizing the scale invariance with different scales of the neighborhoods of the point. Then you're dividing this one into neighborhoods. So you have these 16 subblocks. For each of them, you have an 8-bin histogram that gives you 128-dimensional feature. That's it. Okay. Now you can also learn these kind of feature descriptors, and the way you would do this is, I mean, there's a lot of papers that would do that, but I wanted to just give you a bit of a high-level overview how this works in practice. So the idea in neural network terms, and if you haven't taken like Introduction to Deep Learning or so, this is a lecture you might want to look at to understand this a bit in more detail, but I'm just gonna try to still explain it at a relatively easy to comprehend level. So the kind of idea is you basically have a confident convolutional neural network architecture that tells you that this point and this point, once it's encoded and passed through this neural network, they should have the same feature. Because in this case, you know it based on, like, this is just how this is designed. Let's say you know this and you have these ground truth correspondences. And the idea here is that basically what you're doing is you're taking here, this is in 3D, but it's the same in 2D. So here you can take a volume of 31 cubed, pass it through a convnet, take the same thing in another one, pass it also through a convnet. You're going to get a bottleneck layer here of a 1028 dimensional feature space, and then you just have an L2 distance between those two, and this is then your feature distance, right? So the straightforward thing is, when you train this whole thing, you're just going to say, well, all of the stuff you're feeding in here and feeding in here, if it's matches, if it's the same point, this feature distance should be 0. If it doesn't match, sorry, if it does match, the feature distance should be 0, and if it doesn't match, the feature distance should be 1, right? And now what you're doing is you're treating these two towers of this neural network, you're sharing the weights between those two. This is called a Siamese network. And now what you're doing is you're feeding pairs of matching and non-matching feature pairs in there in order to figure out, or in order to learn a network that basically learns these invariances we've just described before. And the way it learns it is because you're having different viewpoints from the same point that gives you a 0 distance, and you're having negative matches that are random other false matches, basically, that say they give you a large 1 distance in this case, right? And you're training them, and at the end of the day, you're going to get a feature descriptor that is embedded in a test time. You can then go ahead and say, oh, let's see if this matches or not matches. Now, this is very straightforward here, what I did here. If you're looking at state-of-the-art networks, they wouldn't use an L2 distance here. They would probably use something like a triplet loss. So if you're interested in that, Google how triplet losses work for feature matching. There's a lot of stuff out there. And yeah, so this is very popular right now in the learning area. People have been using this for quite a while now, and actually leads to pretty good results. Okay, so if you're looking at some of these results, so often what people do is key point matching. So this is a key point matching result on Sun3D. That's a data set. So here you see basically an error rate. Like if you're using like a large ResNet backbone, you're going to get like 10% error rate. And if you use Surf or Sift, you're going to get something like 46 or 37% error rate. So the error rates for matching features can be significantly reduced with deep learning. But I should say there's a big caveat here. Like just because you have an error rate for matching results does not necessarily mean that you're getting good features for reconstruction. So for reconstruction, there's a little bit more to it. It matters also that you find distinctive matches, right? So these evaluations are typically done on a data set where you have pairs of matches and non-matches, and this tells you how many times you were right and how many times you were wrong. But in practice, when you do reconstruction, you have a slightly different problem. You have actually a 1 to n matching problem. So, and in this case, SIFT is actually still pretty good. And up to date, for most of the structure from motion pipelines, people are still using SIFT. Even though these numbers might suggest otherwise for reconstructions, SIFT is still being largely used. And if you're interested in these areas, making learning-based methods, which I believe ultimately they will dominate this area, that is still not a thing, and this might be still an interesting research avenue, how to make better matches here work. Also for the projects at the end, I can also reiterate it. This might be an interesting point to look at. Okay, well, now we know how to do matching, right? First thing what we do is we detect key points in every image. Next thing is what we do is we find feature descriptors for each of these key points. And once we have features, then we compare them. And in practice, you just do kind of a brute force comparison here. And yeah, it's not just a brute force comparison. I lied a little bit. There's a lot of stuff actually to it, how to make this comparison efficient, how to filter out wrong matches here. Ransack methods is a thing to mention here. There's actually a lot of literature how to get the matching right after you have done feature match. It's actually also an NP-complete problem, right? Every possible combination in principle is valid if you have n frames. But there's a lot of ways how to make this computationally more tractable. Don't want to go into that one. Let's just say it's basically a graph matching problem, right? We have distances between nodes, and we're trying to figure out which edges do we want to keep between the feature matches respectively. And now what we're getting is this matching graph. And now what we have is we have matches established, And based on these matches, we now would love to compute we would like to compute our original SFM, right? We would like to figure out camera poses and camera parameters. And based on these feature matches, there's a process, this optimization, it's called bundle adjustment. And bundle adjustment is based on the reprojection error. So let me explain the idea based on two images. So let's say we have a stereo setting, right? We have these two images, we have the camera locations here, okay? We don't know where the camera locations are, we have to still optimize for them, but let's say we have two cameras, right? We don't know where they are yet. And let's say we have a point X in 3D. We also don't know that point X yet in 3D, right? But these are the two things we want to optimize. So let's say this point X here was matched here with X1 and was matched here with X2. And now what we want to do is we want to go ahead and say, if we're taking this point X, we're projecting it with the current camera transformation of this left image into this space. And then this pi function is the intrinsic transformation. So now we first transform it into the camera space, this point X of this camera, and then we're projecting it into the image. And this gives us a 2D projection of this point X. And let's just say this point projects somewhere here. We know that it should match with X1, and all we're doing right now is we're saying X1 minus where was the projection of this point X here in this camera. And we would like to minimize the distance between these two, right? Between the projection and the matched key point. Okay, I'm doing the same thing for the other camera too, right? Now we're saying this point X here is being matched here with X2. We're projecting it here to X prime 2, and we're saying, well, this X2 minus the projection here, this term here is basically X prime 2, should be minimal, right? Again, just to reiterate, the T's here are the respective frame poses, that's the extrinsics, and the pi's here are the respective intrinsics. Okay, and now what we're doing is we're just adding these two terms up, and we want to optimize for the T's, and we want to optimize for the X's, right? So T left, T right, and X. X is 3D point locations, and T's are the respective camera, the extrinsic matrices. As a quick reminder, here are the transformation matrices. This is our extrinsic. Extrinsic is always a rotation matrix and a translation. So we have here 6 degrees of freedom for each of the T's. This pi matrix, this pi here is our intrinsic. We've discussed it. That's just this 3 by 3 intrinsic matrix divided by the depth afterwards that maps to our 2D projections from 3D, right? So this point maps from X, Y, and Z to a 2D coordinate in pixel space that we can then compare. And this process is called minimizing the reprojection error, right? So we're trying to find an optimization such that we minimize the reprojection here. Okay, now everybody who looks at this will look at it and say, well, yeah, but this is only for 2 images. What if we make this happen for many images? So in practice, we have m images and we have n points in 3D. Right? So now let's say we have more here. Okay. So m is given by the number of input images. That's very clear. N is essentially given by the number of matches that we have between the images and the key points. So in bundle adjustment terms, this is often called tracks. So basically, how many tracks do we have? So if you have 1 point in image 1, 2, and 3, that's a track. So this key point was detected in 3 consecutive images, for instance. Okay, and out of each of these tracks, we know that we want to optimize for 1 point in 3D, right? Okay, so now what we're doing is, so we're taking this term here for 2, and we're just reformulating as a sum over many. So we're just saying, well, we have 2 loops. We have 1 loop that goes over all images, and we have 1 loop that goes over all 3D points, right? So we're saying that every point X in 3D, this point, transformed to the current camera Ti. So every point Xj in 3D transformed into the current camera frame I, projected in the current image I, should match with a 2D key point location xij, right? So for every point in for every 3D point xj, we're gonna have one point in every image in every image I. We're gonna have a j here, right? So this is like ij. So this is like the number of key points we have is number of images times number of tracks. Okay. And this just goes over all 3D points. That's the j variable. This one goes over all images. This is the I variable. Right. So here we have it for 3 images visualized. We see here the respective camera locations. We have the image planes. We see here the 3D points here where they are. And now we are simply optimizing this reprojection error and solve for the transformations t. And we solve for the 3D points x. Okay. There's one small little detail that I would like to mention, because a lot of people might say, but wait a second, this doesn't work, because in practice you will not see every point in every image, right? So sometimes you will only see points into a subset of the images in these tracks. So in that case, you're just missing a bunch of these terms, right? It's a bunch of these sums here we have to just rule out. I want to make it still a little bit easier for the subsequent slides to avoid this masking stuff, or to just assume we see every point in every image. So these tracks would be complete, meaning that every track covers all images. And that makes it a little bit easier on my time now to explain it, but just keep it in mind, right? I'm of course well aware that not every point will be in every image. Okay, but let's talk about this one a little bit more. So again, we have m images and we have n points in 3D. This is the formula we want, or this is the energy function that we want to minimize. And I want to talk a little bit about the number of unknowns. And this is important because we want to know when, every time you're talking about energy functionals like these ones, you want to talk how many unknowns do we have and how many constraints do we have? Basically residuals versus unknowns, right? Okay, so let's talk about number of unknowns. So we have for every camera here, for every image, we're going to have a 6th camera pose, except for the first one. The first one is just the identity. So we have 6 unknowns per camera, translation rotation, times m-1, because we have, the first one is the identity, right? So we have m-1 poses. T1 is the identity here. And we're going to have 3 unknowns for every point. What does it mean? Well, we have an x, y, and a z location in world space that we want to optimize for. There's also the possibility to jointly optimize for the camera intrinsics if you don't know them yet. Let's just say, for the most part, when you're starting these problems, you assume you know them, because this makes it really complicated when you have an intrinsic unknown per camera pair. We'll later see a couple of examples where you have to optimize for the intrinsics as well. But actually, fortunately, in many cases, you know the intrinsics already. Okay, so these are the number of unknowns. So now, in order to make this whole thing work out, we better gonna have enough constraints in order to make sure that we can actually solve it. So how many constraints do we have? Well, it's very straightforward, actually. We have m images and we have n points, right? These are our, like for one point in 3D, let's just assume that point is in every image n. Again, caveat here, but let's just assume for now that's the case. So we have m times n constraints. And now what's important, there's a factor of 2 here. This factor of 2 is because this L2 distance is actually, this is like written as an L2 distance, but these are actually 2 residuals. This is in the x coordinate and in the y coordinate. There's 2 coordinates in image space, right? So we have 2 constraints per point match. So per point per image, m times n, we have 2 constraints, right? This is the number of constraints. Now, is it over under constraint? That's the big question right now, right? So we just have to make sure that 2 times n is greater or equal times what the unknowns are. 6 times m-1 plus 3n for the points, plus whatever, how many intrinsics we have to optimize for, right? And I can say one thing to that. in practice, you just don't want to make sure this is equal. In practice, you want to make sure this one here is significantly larger. This makes the optimization problem actually work because there's also a lot of local minima. In practice, you want to make sure this one is a lot bigger. This is really important, actually. But yeah, is it under constraints or over constraints? And you can do the math here, right? This one here grows only linear, the number of unknowns, with number of points in images, whereas this one grows quadratically. So we're getting, the more we're adding, the more this one here grows, the better for us, because right, the more constraints we have. That's good. Okay, so between two calibrated images, meaning you know the intrinsic calibration between those images, you need at least 6 correspondences. But there's a few catches now. They also need to be not linearly dependent. If they're all on a line, that doesn't work. Then these constraints all tell you the same thing. You need to have they need to be linearly independent. Otherwise, you also can't solve it. But you can do the math, right? Like, you need to make sure that you have no collinearities, and you need to make sure you have enough of the matches, basically. Yeah. So you need at least 6 correspondences between two images to over-constrain it, and then the more images you have, the better, because this one scales basically very well, because this term here is quadratic, whereas this term here is linear. Right. So this so far is structure for motion. In this lecture, I have a few more things to talk about. In principle, what we haven't talked about is how do we actually optimize these terms. This is something we're going to do in the next lecture, but today we're just going to leave it there. The goal basically is to optimize these kind of points, these kind of equations. Okay, but the bottom line so far is we only obtain a sparse set of points. Structure for motion, by the way, is also relatively slow. And when anybody wants to do structure for motion, the key is always to find good features. If you have perfect features, the whole problem becomes really easy. And the second challenge, finding good initializations for optimization. That's something people can figure out, but finding good features, that's difficult, actually. That's still an ongoing problem in the literature. Very, very difficult, because you have so much variance between different views. Relighting is critical, right? Not so straightforward. Okay, I'm going to show you a couple of examples of structure for motion. Example research papers and applications, so you can also do a bit of further reading beyond this. And one of the things that's pretty cool is this. This is called the Bundler framework. This is something that Noah Snavely did in 2010. So it's not that old, right? It's like 12 years old now. And what he and his collaborators did is basically they had a bunch of images from the Roman Colosseum. They were crawled from the web, actually, funny enough. And then they reconstructed the Colosseum here. They got this point cloud. And this is kind of a very cool example. This bundle is one of the first open source softwares that people used for structure for motion. It's still online. People still use it, actually, today. There's also more applications to that. I found this one pretty cool. This is an application from Enquist et al. In 2011. This is kind of a very nice demo pipeline for structure for motion. So they took a bunch of images of this castle, and they do the pipeline what we said. First, they identify key points. So here they have the key points in all of these images. Now they search for correspondence between those key points. Now they have correspondences. They do this between every image pair. Now they compute the camera positions and 3D point positions based on bundle adjustment. This is basically what we've just learned, right? So they're optimizing for these points in the camera poses at the same time, based on the reprojection error. And now they took these images of these close to 700 images. And now at the end of the day here, you see the visualization. You see these little things on the side are the camera locations that were optimized for. And then you see the point cloud of this castle. And I think that's kind of cool, right? You just took a bunch of images and you get now your 3D point cloud and camera parameters for this little castle. Okay, another very popular example is building Rome in a day. That's also from the same group, from Noah Snavely. They took the bundler here and they crawled web images from the Colosseum, which is pretty funny. So they basically, I think they used Flickr images. And I think they checked for, I mean, in principle, I think they can optimize for intrinsics too, but I think for these reconstructions, they used images which had EXIF tags. So for each image, I think they knew the intrinsics at least. And then they were using all of these crawled images with sufficiently high quality of this Colosseum on Flickr. And then they basically optimized the structure for motion pipeline, and this is what they got at the end of the day. Here's another cool example. This is the city of Dubrovnik in Croatia. So here they took 5,600 images. And you see, this is actually a sub-selection of the images. Originally, they had like almost 60,000 images. But they took only a subset because they wanted to make sure they get good matches, so they would and good quality. So they did heavy filtering, and it was pretty funny. This was 2011. This took like 23 hours and on like a massively parallelized multi-core machine. Nowadays, there's probably faster ways to do that. Nowadays, it's pretty funny. It's like only like 12 years ago, right? Or 10 years ago. And yeah, it's pretty cool. But this is very exciting, actually. Right now, you can basically reconstruct the city, which is this tourist attraction, right? Because that's the reason why there's so many images. And it's pretty cool. Now you're getting this 3D model out of it, of the city. And for those with a good feature detector, they will, of course, immediately recognize it from Game of Thrones. This is also the city that was King's Landing in the series. And yeah, I don't know. I found this pretty cool. Okay, there's a couple of more applications I wanted to say that work on top of that. So one thing you can actually do with structure from motion now, you can do image-based rendering. So instead of just using the point clouds, what you can do is you can now use the points to, because now you have the camera locations, you can now take the point cloud and where you are, you just look up the respective images from the current poses. So this is something you can see here. And you can basically now move around in 3D, and the software will automatically select the closest image in 3D space that is closest to what you're doing. It's kind of this image-based rendering, like Google Street View is doing that as well. And this is what's happening here. So now you can browse the images based on the current camera location on where you are. Here's another example on the right. Let me show that one here too, right? So here they also did some blending between the images, but on the background, it's kind of doing structure for motion in order to optimize for the camera parameters. I should say this is like 2006, so this is also relatively old by now. In this lecture, we'll go a bit further. There's a lot of new things to that now and how you can make this all better. But the core skill, you need a good pose optimization from a structure for motion pipeline. Another example I found pretty cool is this Hyperlapse. So if you, for instance, wearing a GoPro or something like this on your helmet while doing some stuff, so the idea is a lot of people wanna when they're biking, walking, doing some sports, right? They want to have first-person footage being recorded, and if you do that, it looks something like this here, right? You see that the camera motion here when you speed this whole thing up, and when I have a time lapse is like almost unparsable, right? It's like super jittery and so on. And one thing what you can do is you can do this hyperlapse, and this is the result here. You have these smooth transitions between the images here. So they do this video stabilization by basically running a structure for motion pipeline in the background and then using the optimized trajectories to do the video stabilization. Again, here's like the naive time lapse, which is like super shaky, and then they do this hyperlapse, which is a very smooth transition through the camera path here. Okay, so these are a few applications. The reason why I'm mentioning them is to this image-based rendering, which uses structure for motion at the backbone. We'll get to this later, and we'll do a lot more around it actually. But now I wanted to talk a little bit about multi-view stereo. And a lot of people actually confuse structure for motion with multi-view stereo. The idea of structure for motion is only what I just said before. Structure for motion just estimates camera parameters and a very sparse set of key points in 3D. Sorry, it estimates the positions of the key points in 3D, but it doesn't give you any surface and it's not very dense. But the idea of structure for motion is you take the idea of multi-view stereo is you take the results of structure for motion. Basically, you take the 6 poses of the images, you take the estimated 3D points of the sparse point clouds, and now what you would love to do is you would like to estimate a much, much denser surface. Not just at the key points, but pretty much everywhere we'd like to estimate a surface point. And in multi-view stereo, there's actually many variations of semi-dense, dense, and so on. There's also a bit of a name ambiguity, right? Often people call it dense photometric multi-view stereo and stuff like this. But in this lecture, and generally I think, you know, in our community, when people talk about multi-view stereo, they mean a dense point cloud reconstruction that takes as input the sparse SFM reconstruction. So how does it work? Well, in practice, it's a very simple idea. You just do dense stereo matching between every frame pair, right? We can do that now. We know how stereo matching works because we have the alignments, we have the intrinsics, and then you get a lot of noise out of it, but between this noise, you somehow vote for the results which you think are reliable and ideal. And this is often, people formulate this, instead of doing this in a pairwise fashion, they sometimes try to do this in a global fashion too. So they're solving for all disparities simultaneously. There's a lot of papers that use Markov random fields in this area. So they have kind of a matching cost term and pairwise term. And then they're trying to globally propagate these cost function updates. Semi-global matching is also a very popular method that is being used often. It basically makes it tractable. But as you can see, if you think about it, if you're doing this global optimization for multi-view stereo, this is it's basically also an NP-complete problem, right? So you want to know every point in every image, which other point does it match, then you get disparities. But the idea is, of course, you have to approximate this in one way or another one. The semi-global matching is a very popular one, but there's many ways to do this actually in order to make this more tractable. But this might be a paper you might want to look at, but I just wanted to give you a bit of an insight, like structure for motion at the top, and at the bottom you see multi-view stereo. So you see a bit like what sparse versus dense reconstructions mean, right? So the number of points you're getting is at least an order or 2 orders of magnitudes higher. Now, the question is, why do you still do that? So this is a method by Johannes Schönberger, pixel-wise selection of unstructured multi-view stereo. So they get pretty good results actually in their pipeline. And the question is, why do we do that? Well, of course, we want to get a better approximation of the surface from which we later can do some sort of surface reconstruction, right? So the overall pipeline, for the most part, looks something like this. So first you do structure for motion, then you do multi-view stereo, then you use this dense point cloud, you estimate normals for the points, can use this with a PCA. And by the way, if you don't know how to estimate a normal from a point cloud with a PCA, you should look that up. This is a really important thing to do. This is something I like to ask in interview questions. Yeah, this is something you should know. And then what you do is you feed these dense point clouds with the normals into surface reconstruction, surface fitting methods, for instance, the Poisson surface reconstruction. And once you have the Poisson surface reconstruction, you get a triangle mesh out of it, and then you can texture the final surface. Let me actually write this down. Maybe we can have an exercise about normal estimation from point clouds, but this is important. Okay, so Poisson surface reconstruction, I'm not going to go into detail. I hope you all looked it up because this is the reading homework from the last time, right? Remember, Poisson surface reconstruction has this indicator function. You're solving this Poisson equation. The input here is the point cloud with normals, and the output is this implicit indicator function from which we can then extract the mesh respectively, right? Okay. And basically this is what we're getting, right? So after solving the Poisson equation there, and after extracting the mesh, we're going to get actually some reconstructed mesh out of it. Okay, and this is the typical pipeline that people are using. So first you do structure from motion, then you do multi-view stereo, and then you do some sort of reconstruction like Poisson on top of it. Again, Poisson we've already looked at, SFM MVS we've looked at today, and this is a very common pipeline that a lot of people are using. So Pix4D is a commercial software for this. Agisoft Photoscan, I think they renamed it to Meta Photoscan or Agisoft Meta or something like this. But this is also a commercial tool. Colmap is a very popular open source one that does that pipeline, and you basically see how this works in practice right here. Input images, then you get a sparse point cloud, you get a dense point cloud, you run Poisson, looks something like this, you're gonna texture it, and then it looks like this at the end. So I wanted to show this video because I found this cool. Right, so here we take a bunch of images of this model, and at the end of the day, you can actually get reconstructions that look like these ones. This is the sparse point cloud here. This one is estimating the camera poses and the points. This is how it looks when it's sparse. This is how it looks like when it's dense. Okay, this is after the Poisson surface reconstruction. This is after it's being textured. And then here's a bit of cleanup being done as well. But yeah, looks pretty good. And afterwards, we're getting a 3D mesh out of it. Okay. All right. So this is basically the pipelines for multi-view stereo and reconstruction from multiple images. For the completeness, I also want to mention the relationship to things like SLAM. You might have heard that. So SLAM is the idea of basically doing structure from motion plus multi-view stereo in real time as you're getting the images as input. So the idea is instead of having all images available at the same time, you have like a webcam that goes through a room or on a car or whatever, and then you want to do SLAM, which means you do simultaneous localization and mapping. So the idea here is very similar than SFM and MVS, except that it's online and the model is built up incrementally, right? So it takes kind of the stream of RGB images as input, meaning that when you get the first images and you want to optimize the poses and the intermediate point clouds based on these images, you don't know the future frames yet, basically, right? And the other aspect when people talk about SLAM is there's typically a much smaller compute budget available, right? So typically people want to do this in real time, and they don't have a lot of time to do things like SIFT matches or so, which is expensive. But you can still make it work. Okay, often only frame-to-frame tracking, meaning that often they don't do a global optimization, but they just use the current estimate and then they're adding more and more stuff to it afterwards. Okay, wanted to show a few examples of SLAM. A very popular method is this method by Jacob Engel, LSD SLAM. That's a method that was done actually at TUM. It's a very popular method. It was published in 2014. And the idea is basically they are having a lot of ways to kind of balance the compute budget here between key point finding, structure from motion, local bundling kind of between keyframes, and then updating the poses globally and locally in kind of this hierarchical keyframe fashion, right? So they don't use all the frames, they use only important frames, and so on. So there's a lot of detail and engineering efforts to make this work. This is kind of among one of the state-of-the-art methods, actually. And yeah, here you see a couple of more examples. Again, this works all in real time, and I think that's actually really, really impressive what you can do nowadays. Yeah. Okay. Another very popular SLAM method is Orp Slam. Very similar idea. That's a little bit later done. I think this is probably the state of the art now, what people are using. It's also open source. You can download it. And they also do similar pipeline, right? So they basically extract keyframes, and then they kind of save a bit of compute budget with that. So the core concept of these SLAM methods is it's very similar to bundle adjustment. They extract these keyframes on a dynamic basis, and then they do bundle adjustment on a local keyframe window. They often use Orp features, hence Orp Slam. This is how they originally started. But the output then is poses plus as far as point cloud, and then there's various semi-dense SLAM methods to get basically denser methods, kind of trying to replicate the multi-view stereo part, which is traditionally speaking very slow and so on. So yeah, maybe have a look at the LSD SLAM paper. I think that's a really cool paper. That's something you might want to look at. You see that there's quite a lot of engineering. I think most of the terminology to understand that paper you should know after this lecture now. So this might be a good read and a good lookup. We're gonna talk a little bit also about Rgb reconstruction, because there's also a lot of SLAMs in it. So basically today we talked about giving multiple images, but I want to talk a little bit more in depth about Rgb reconstructions, how you would basically do SLAM on a Kinect based on the tools that we have learned about. So in this case, we already have the depth data that makes things a little bit easier to do things real time, and you get also dense reconstructions. A typical approach here is frame-to-frame tracking or frame-to-model tracking, and then you accumulate the depth data in a model, like an implicit surface. And this is kind of a nice pipeline here. So what's happening here is basically there's an input depth map. Based on the input depth map, there's going to be a camera pose estimation. Based on the camera pose estimation, the depth map is being fused into a global model. This is the model data. And based on that model data, you estimate then the poses again for the next frame. So imagine the way this works. The first frame is the identity. That's going to be your model. Then you get the second frame. The second frame is compared with the current model, which was the first frame. It gets your pose. And then based on that pose, you update the model. Now the model has parts from the first and the second frame. You get the third frame. The third frame computes a pose to the model, which was based on the first and second frame. Based on that camera, you fuse the third frame into the model, and then you update again. And this is kind of iterated on the fly. And one of the methods that did this was this very famous Kinect fusion methods. They kind of published it mostly along with the Kinect when it came out, and they could do stuff like this here. So they have an input depth map. And based on this input depth map, they're basically updating this model and estimating the camera parameters on the fly. And they're getting they're using a TSDF as a representation here. This one will go into a little bit more detail in the next lecture, but I wanted to show it what you can do with it, and I found this pretty cool. Okay. Yeah, and this, like, the model quality is actually quite high. So I think I'm a big fan of these kind of frame methods. I think that's pretty cool. You can get pretty good reconstruction results out of these ones. One thing though, what these methods don't do, they typically struggle with loop closure. So because they do only frame to model tracking, right? They take the current frame, align it to the model. Every time they do this, they accumulate a small little error. And when you take a camera path and go around here, you have to figure out how to address these loop closure problems. And these loop closure problems is actually really difficult because in a real-time reconstruction method, you have to do global pose optimization and fix your model afterwards. So really what you want is this one here. And this is what you want to optimize for. So even if this is not in an offline, even this was not in an online setting, but you wanted to do it offline, it's not so straightforward. But basically what you can do is you can do the same trick what we have seen before. So instead of doing bundle adjustment in 2D, you can do a thing called, well, I kind of call this Rgb bundling. I'm not sure if there's a better term for it. But the idea here is very straightforward. So now instead of having a reprojection error with the previous bundling, in order to do a global pose optimization on RGBT data, what you do is you say, you have these correspondences with feature matches. That's the same thing like SFM. But the difference with RGBD bundling is that these points here, per feature point that you have here, you already have the depth data. So these points are in 3D. These PIK and PJK, they are in 3D already. So the advantage in RGBD bundling would be that you can already do an error term in 3 dimensions. So you don't need to have this reprojection error with the reprojection matrix. In fact, there's not even a projection matrix in this whole bundle term here, right? This is just comparing 3D points. And what you want to make sure is that if you're taking a point in 3D, you transform it into world space and then transform the matching point also in world space. You want to make sure that these 2 points then in world space, they both match. That's all you want to do. So it's very straightforward in principle. And you can globally optimize that and kind of do sparse bundling on RGBD data. You can do a little bit more here. You can also do, using kind of, like I call this dense bundling, you can not only take the key point matches, but you can actually take every single depth value. And this looks a little bit complicated, but I want to walk you through quickly what this means. We'll go to this in a little bit more detail in the next lecture, but I wanted to walk you very quickly through what this means. So between all frame pairs, you're going to look at every pixel between all frame pairs. And what you do is, let's start here. You take a point in one frame, you project it to world space, project it to the other frame, you project it into 2D in the other frame, you look it up in the depth map, you project it back, you project it to world space, and you project it into the respective other frame, and then you're comparing it to the original point PK, right? So this point PK from a given frame, if you're projecting it to another, if you're projecting this one to another frame, projecting it in 2D, looking up the depth value, projecting it back again to the original frame, these two have to match, right? And you're basically optimizing for the T's here, only for the transformations. And then there's this little small detail here. Typically you do this not on a per point match, but you do this on a per normal match. And you multiply it with the normal of the point. So it's a point to plane distance that we're doing here in this depth term. It looks a little bit complicated, but think it through. Maybe take a piece of paper and try to visualize what all these transformations mean. If it was too fast, just go back in the video and do it again. But this is a very, very instructive moment because you need to understand, if you understand all the spaces, like frame space, screen space, image space, camera space, and world space, then this is straightforward to you. The only difference here, these are the intrinsics, this is the depth map of the target, and these are the normals. You can do the same thing in color space. You can also take a point at the point P, project this point P into the other frame, project it into image space, look up the color value, compare it with the color value at the point P in my current frame. And you just want to minimize the difference between those color values. And instead of using the distance of color values, you typically use the gradients of the color values. That's a little bit more robust when it comes to optimization. Okay, we're going to talk about this one a little bit more later, but I just wanted to say there's also dense options in depth, because now you can reproject points from one frame to another one because you actually have 3D data. This one gives you better poses than just standard 2D bundling. Okay, let's have a look again, a quick recap here what we talked about today. We talked about these two terms. We talked about bundle adjustment in 2D. We talked about bundle adjustment in 3D. And the idea here is we have to solve these terms. So we have to talk about in the next lecture about the optimization, how to figure this kind of stuff out. This is what we're going to talk into a lot more detail. I also wanted to give you a reading list if you're interested. This is a good overview of 3D reconstruction methods. I like this a lot. Can have a look at it. Gives you a lot of good literature overview. I also wanted to give you some reading homework. I would like you to have a look at this Schoenberger paper, Structure from Motion Revisited. This is basically the Colmap paper. You can also try and run Colmap on a toy example. This is very easy to get to run. They even have binaries. Actually, also have a look at the LSD Slam paper. That's a very good paper too to have a look at. So these are the two papers to read. Structure from Motion Revisited and LSD Slam. And run Colmap. Try it out on a bunch of images, see what you get. And next week, we're gonna talk into the optimization methods. Thanks a lot for today. See you all next week. Bye-bye.